Welcome to Shanti-Peace for Mathematics. Have a good day to all of you. In the previous video, we have talked about necessary and sufficient condition for differentiability, which tells you that if f is differentiable at point z0, if and only if f is a function as u plus iv, then the partial derivative, that is ux, uy, vx, vy, are exist and continuous at x0, y0 if this z0 is represented as x0 plus iy0, and the second one ux is equal to vy and uy equal to minus vx. These are known as the CR equations. So we have talked about the necessary and sufficient condition for differentiability in the previous lecture. We also seen that if you remove this condition, then the CR equation does not imply f is differentiable. Now also I gave you one example to discuss in the previous lecture, that f of z equal to 1 upon z cube. If z is not equal to 0, then I have asked you to prove that this function is differentiable. So those who have not tried for that, kindly do the try for it. Pause the video and do it, this example. So what you have to do, actually you have to check that you want to check that f is differentiable. That means you have to verify the first order partial derivatives are exist for this function and the CR equations are satisfied and the first order partial derivative are continuous at that point. Now when you are trying to solve this example, what you are doing is you are calculating what is the real and imaginary part of this quantity. That means you are doing this x minus iy cube here is there, and then you are multiplying and divide by x plus iy cube. So this will be x square plus y square raised to cube, and then you expand this numerator via binomial expansion, and then you will have to take the derivative of those terms. That means whatever the real part you will have, the denominator will contain x square plus y square raised to cube, and then numerator you will have something plus I also you have here, and then you have to take its partial derivative with respect to x and y. So it's more difficult, more calculations will be there. So the idea is, if you can convert this function into the polar coordinates, that is x is equal to r cos theta and y equal to r sin theta, then what is your f of z in terms of polar coordinate, that is r cube e raised to I 3 theta. If I substitute z is equal to r e raised to I theta, then you will have a real part as 1 upon r cube. This we can write as cos 3 theta minus I sin theta, that we can write. So you will have a real and imaginary part very quickly. So your real part will be 1 by r cube cos 3 theta, and the imaginary part v of r theta is 1 by r3 sin 3 theta minus. Now so if you want to do that, then the CR equation in Cartesian form, it's represented in this manner. But what are the CR equation in polar coordinates, that we don't know. To solve these problems, we are converting our CR equation, that is ux equal to vy and uy equal to minus vx. They are in Cartesian coordinates. We need to convert them into the polar coordinates. So with that things, you know that u is a function of x and y, and x and y are the functions of r and theta. So you have this chain, and if you want to calculate del u by del r, that is derivative of u with respect to r, then you have to go via two paths. One of them is this, another one is this. So this will be del u by del x into del x by del r plus del u by del y into del y by del r. Similar manner, we'll have del v by del r equal to del v del x into del x by del r plus del v by del y into del y by del r. Same way del u by del theta If you have, then we can write as del u by del x into del x by del theta plus del u by del y into del y by del theta. Also we have del v by del theta will be del v by del x into del x by del theta plus del v by del y into del y by del theta. If I call this first equation as 1, this will as 2, this one as 3 and this one as 4. Now we need to find out what should be this del x by del r, del y by del r. So if you substitute that value, so you know that x is equal to r cos theta and y is equal to r sin theta. So that is del x by del r will be cos theta, del y by del r is sin theta, del x by del theta is r sin theta, and del y by del theta will be r cos theta. This is minus. So we have this, so we can substitute this value into each one of the equation. So let us write down one by one that equation form it's converted into. So now you will have del u by del r, that I can write as ur, which is cos theta del u by del x plus sin theta del u by del y. Then you will have vr, that is del v by del r, that you can write as cos theta del v by del x plus sin theta del v by del y. Then you will have u theta, that is del u by del theta. So as per the things, it is del u by del theta, del u by del x into del x by del theta. So that is r sin theta plus r cos theta del u by del y. And the second equation you will have v theta will be del v by del theta equal to minus r sin theta del v by del x plus r cos theta del v by del y. We call this equation as 5, 6, 7 and 8. So in the equation 6 and 8, you will use the CR equation, that is ux is equal to vy and uy will be minus vx. You use that. That means whenever v is there, you just convert them into the u. So this quantities I may convert them into u and rewriting the equation. So using CR equation in 6 and 8, we get Vr equal to del V by del R equal to, so you can see that in this del V by del X I can write as minus Uy, so that is minus cos theta del U by del Y plus sin theta del U by del X, and V theta you can write as del V by del theta, which is R sin theta del U by del Y plus R cos theta del U by del X. If you call this equation as 9 and 10, now just see the equation 5 and 10. Let us rewrite this equation 5 and 10. So you just see that what is 5 equation. Let us see that. That is UR is equal to cos UX plus sin VY. So that is UR equal to cos UX plus sin UY. And this equation 10, we have V theta, and if I common out this R from this, so that is R, and I'm just writing this cos UX first, so it is cos theta UX plus sin theta UY. So if I see that this quantity is nothing but the UR, so that's why it is RUR. So finally what you will have is UR equal to 1 pi R V theta. Now you just see the equation 7 and 9. So let us see what is equation 7 is u theta equal to minus r sin theta ux plus r cos theta uy. And what is equation 9? That is Vr equal to minus cos theta uy plus sin theta ux. Now you say that if r is common out from this two quantity, that is minus, if I minus r is common out, then it is sin theta ux minus cos theta uy, which is nothing but the Vr. So it is minus Vr. So finally what you will have is Vr equal to minus 1 upon r u theta. And these two equations, that is the nothing but they are the CR equation in the polar form. So CR equation in polar form can be written as ur 1 upon r v theta and Vr minus 1 upon r u theta. So these two equations are known as a CR equation in polar coordinates. So this is the one way to compute this polar coordinates. And if we can assume that if you have a function which is u plus iv, where u and v are functions of r and theta, and its first order partial derivatives are continuous at the point z0, that is r0 e raised to r0, that is non-zero number, and it's satisfying this CR equation, then you will have f dash of z0 will be e power I theta ur plus I Vr. That means it is a differentiable function you will have. Another way to represent your CR equation in polar coordinates in the simpler way is this. Suppose you have a function w equal to f of z which is differentiable. So, and it can be written as u plus IVR, where u and v are the functions of r and theta. If you take the derivative and if you substitute z is equal to r e raised to I theta, so if you differentiate this equation with respect to r, so it is f dash of r e raised to I theta, and the derivative of r e raised to I theta is e raised to I theta. The derivative of u is ur plus I Vr. And with respect to theta, if you do the differentiation of that, that is f dash of r e raised to I theta into r e raised to I theta into I equal to, now derivative of this u, that is u theta plus I v theta. Now you just see that f dash of r e raised to I theta into e raised to I theta can be written as 1 by r u theta, I is there, plus I by I it is 1 v theta, so that can be written as 1 by r v theta minus 1 upon r u theta I, because you multiply and divide it by I, so I square will come in the numerator and that will become minus 1. And this equation and this equations are the same, so you can say that equation 1 and equation 2 are the same. So if you compare the real and imaginary part, you will have ur is equal to 1 upon r v theta and Vr equal to minus 1 upon r u theta. That completes the proof in another manner, and which also tells you that what will be the value of f dash of z. So the f dash of z can be calculated as, according to that, it is into e raised to I theta equal to ur plus I Vr. So this u e raised to I theta you can take another side, so it is f dash of z is 1 upon e raised to I theta ur plus I Vr. This is the one way to represent the derivative of a function into the polar coordinate. So let's have that example which we have started in this lecture. That is f of z is 1 upon z cube we have. Then we need to calculate what will be the, whether this function is differentiable or not. So for that you should check whether the CR equations are satisfied and the first order partial derivatives are continuous. So if you compare with r e raised to I theta cube, if you substitute z is equal to r e raised to I theta, we'll have this. So if you can see that the real part will be cos 3 theta cube minus 1 by r cube is here sin 3 theta I. So u of r theta is 1 by r cube cos 3 theta. V of r theta is minus 1 by r cube sin 3 theta. So you will have u r. So derivative of minus r cube is minus 3 into r raised to minus 4 cos 3 theta. That can be written as minus 3 upon r raised to 4 cos 3 theta. U theta will be minus 1 upon r cube sin 3 theta. Then V r is again minus 3 upon r raised to 4 sin 3 theta, and V theta is minus 1 upon r cube cos 3 theta into 3. Here is also 3 came. This I can write down into this form as minus 1 by 3 r cube cos 3 theta into 1 upon r, so that is 1 upon r v theta, and this Vr equal to minus 3 r raised to 4 sin 3 theta can be written as 1 by r minus is also common. This will become plus actually. Here you will have a plus. So that's why this is minus 3 by r3 sin 3 theta. So that we can write as minus 1 by r v u theta. So you will have here u r is equal to 1 by r v theta and Vr is equal to minus 1 by r u theta. Hence the CR equations are satisfied. Also it's involve the trigonometric function and the polynomial in R, so that's why they are continuous. So we can say that this function f of z, it is 1 upon z cube, is differentiable except 0. So in its domain it is differentiable function. Now next task we are doing is proving the Laplace equation into the polar form. So what is the Laplace equation into Cartesian form is uxx plus uyy equal to 0. So this is known as a Laplace equation. So what is example is, if f of z is a function, that is p of r theta plus I q of r theta is a differentiable function on a domain D, then this p and q are satisfying the Laplace equation into the polar coordinates, that is del square p upon del r square plus 1 upon r del p by del r plus 1 upon r square del square p by del theta square equal to 0. Then prove this. Also for q we have the same thing, that is del square q by del r square plus 1 upon r del q by del r plus 1 upon r square del square q by del theta square. Since the function is differentiable at this point, so it has to be satisfying CR equation. So what is the CR equation? Del p by del r equal to 1 upon r del q by del theta, and del q by del r equal to minus 1 upon r del p by del theta. Now this function is continuous, so it is differentiable. So I am taking the derivative again because this expression contains the double derivative. So I am just differentiating this expression with respect to r, so that's why we will have del square p upon del r square, which is the derivative of this with respect to r. So if I apply the product rule here, 1 upon r is as it is del square q upon del theta del r plus del q upon del theta as it is. Derivative of 1 upon r is minus 1 upon r square, and if I differentiate this, del p by del theta equal to minus r del q by del r. If I write down this equation into this form, and if I differentiate this with respect to theta, because it's also involved the second derivative of that. So if you differentiate this with respect to theta, you will have del square p by del theta square. R is constant with respect to theta, so that is why it is del square q upon del r del theta. Now I'm starting with RHS. What is RHS? Is del square p upon del r square plus 1 upon r del square p upon del r plus 1 upon r square del square p upon del theta square. Now let us substitute these two values which we have calculated. The first one is this, second one is this. Substitute them. So that is 1 upon r del square q by del theta del r plus minus 1 upon r square del q by del theta plus 1 upon r del p by del r plus minus, because del square p by del r square is, so it is minus 1 upon r square del square q by del r del theta into r is there, so 1 r is cancelled out, and so you just observe that these two quantities are cancelled out due to qr and q theta are continuous, so that's mixed partial derivatives are same. And for this two, you just apply the Riemann equation, that is PR, you know that it is 1 upon r q theta. So if you substitute PR, that is del p by del r as 1 upon r q theta, so that is, here you will have 1 upon r q theta, so it is plus r square, so it is, you will have minus 1 upon r square del q by del theta plus 1 upon r square del q by del theta using the CR equation, so that will give you 0. So we can say that P satisfies the Laplace equation of a polar form. Similarly, you can prove that Q satisfies the Laplace equation of the polar form. With that, I am giving you certain examples here. The first one I am giving you, check whether the following functions are differentiable or not. That is, f of z is equal to under root of r e raised to I theta by 2 if theta is between minus pi and pi and r is positive. And the second one, f of z is equal to e power minus theta cos ln r plus I e power minus theta sin ln r if r is positive and theta is 0 to 2 pi. So with this, let us recall what we did in this lecture. In this lecture, we have discussed about the polar form of a CR equation. The polar form of a CR equation is UR equal to 1 upon R V theta and VR equal to minus 1 upon R U theta. And f dash of z can be represented as e power minus I theta UR plus IVR. So in this manner, you can calculate what is the derivative of a function in polar coordinates. Also, you can check the necessary condition. That's it for this video. If you have liked this video, please press the like button. If you have any comment, suggestion or a question, please drop down in a comment box below. Till then, bye bye, sayonara.